Here we are at part 9, and we're actually looking at page 617, the endocrine system. And we just looked at this page right here with short-term stress, which it could be good or bad. If we're engaged in a sport and we're sprinting on the bicycle or sprinting as a runner, then we're enjoying our activity, possibly a basketball game or some other event, running up hills and down hills and that sort of thing, and using our epinephrine. Over here we have the long-term effects, and here we're observing the outcome, as I indicated before, of aldosterone, mineral corticoid, or cortisone, the glucocorticoid. And so one of the things I wanted to bring to your attention is that those of us who have estrogen in differing amounts at different times of the month experience a bit of puffiness at certain times when the concentrations are fairly high of estrogen, maybe somewhere in the mid-month region, and then after ovulation. And because of the nature of the steroid hormones, it's possible for estrogen to be mimicking aldosterone. It has aldosteronic effects. And so women of childbearing age with significant amounts of estrogen in their monthly cycle will experience this sort of crossover effect here of estrogen. We're coming into the pineal gland. All animals throughout the world respond to sunlight and nighttime, and some are more awake by night and some are more awake by day. In either case, whenever they do need to go to sleep, they will experience a shift in light, one way or the other. Some animals are more awake by night, like owls or fruit bats, and then some animals, including the human, are more awake by day and asleep by night. And so as night falls and the light reduces, it's picked up by the optic chiasma, and there's a suprachiasmic portion of the hypothalamus that picks up that signal and then goes to the epithalamus at the opposite side of the thalamus, the pineal gland. And the pineal gland specializes in the production of melatonin. Melatonin is the, the start of the race, shall we say. It doesn't actually cause sleep. It simply initiates the moment when we are most likely to have the steepest drop from consciousness to sleep. And if that's the case, then we get to have a very deep sleep. And melatonin is the molecule that does that. If you're trying to rectify your sleep, then sometimes you have to go out, and maybe you've moved to a different time zone, and light is different for you now. And so you'll need to go out in the light and actually observe the decrease in light over time, and then you get your natural melatonin. There is somewhat of an experiment going on in the world in which the world is using melatonin as an over-the-counter supplement, and this may or may not have positive effects, but nevertheless, it's not actually a drug that induces sleep. Instead, it's a molecule that marks the time when falling asleep is likely to have the greatest benefit. Okay, so then we press on to the pancreas. The pancreas is mostly made out of, here we are on page 618. The pancreas is mostly made out of the cells that you see outside here on the edges of this picture. These are the endocrine producing cells. And then occasionally within the context of the pancreas, we have these regions which are laced with capillaries. And we have two different cell populations there. One is going to be the alpha producing, the alpha cells which produce glucagon. And then we have the beta cells which then produce insulin. And you'll see that they're pointing here to the red staining cells. The acid stain is the red stain, and that's the alpha. And then these other sort of more faintly staining cells are the beta cells. So alpha for glucagon and beta for insulin. And these are our islet. This is referred to then as the pancreatic islet or the islet of Langerhans. Okay, so they discuss both of these molecules. Glucagon, part of the nighttime cocktail in general, plays a role with growth hormones, factors, and cortisol, and provides glucose as energy in the blood. The glucose is stored as glucagon. The other option here is, and also where's the glycogen coming from? It's coming from the liver for the whole body. It's coming from muscles, so muscles can use their glycogen as you go through the day. The kidney has glycogen stored for itself, whereas the liver is actually storing for the entire body. And we learn how to store certain levels of glucose as glycogen based on the past 8 months of activity. If you've not been doing much, then the liver will not store very much. If you've been extremely active, then the liver stores much more. Then we have insulin, the daytime cocktail to go with epinephrine and thyroxine, and one in which you are seeking food. And ultimately, over here we have the effects of what happens when insulin is released and we've had a meal. It's usually in that conjunction that it happens. Number one, we're going to catalyze oxidation of glucose for ATP production in the cells. So the cells that are most immediately in need of the glucose take it up, and they metabolize the glucose and produce ATP. Okay, then number two, when we have more than what is required for that immediate need, we join the glucose molecules together by the thousands, and we produce a fairly simple polymer called glycogen. Okay, and then the third thing, after we've produced the amount of glycogen that we need for a day's worth of energetic output, whatever your calorie for the day is, maybe it's 2,000, maybe it's 3,000, whatever it is, then after that we're going to convert all the rest of the glucose to fat, and that's going to be stored in the adipose tissue. So we have a little 1, 2, 3 with regard to that. We have a huge homeostatic imbalance potential in the form of diabetes, and I'm going to do a separate workup on the paper. I have 2 review papers from the journal called Cardiovascular Diabetology, in which I'm going to look at diabetes. But for right now, there's two types of diabetes: type 1, type 2. Type 1 diabetes is an autoimmune problem in which the beta cells, that's type 1 here, is when the beta cells are destroyed through autoimmune functions. And then type 2 is where we have a situation in which we don't have enough insulin, or the insulin is not working properly and the tissues are not sensitive to it. So that's an interesting possibility. It could be that a person has become obese, and therefore the size of the body matters because only so much insulin is produced, and it might not be able to deal with the change in volume. The same thing would happen with women of a slight size, of a petite size, who then become pregnant. There are many Asian women who become pregnant, and they pick up as much weight as any other woman of any given stature, because they're producing a baby of a certain size, 6 to 8 pounds, and it requires all of the supportive tissues that are required in any other woman to do it. And so a woman who only weighs 90 or 100 pounds is not necessarily going to fare well in terms of her own molecular support. So she might not have enough insulin, and this is called gestational diabetes. It can be very dangerous, and it needs to be looked at carefully. Over here we have the signs of diabetes, and the signs of diabetes are described over here, where we have an increase in blood glucose in all nutrients, actually. We have actually starvation, because they're not being taken up by the cells, and so there's a need for more and more food, even though it's already in the blood. And then ultimately there's a breakdown of fat to ketones, and that smell has the smell of acetone.